Hello!
What the heck?
Tagon.
So if you saw the last video about decomposing a square into a bunch of triangles, I've got a slightly simpler task for you. If you've seen the short that I will have posted recently, then you know what the question is. The question is, how many squares can I decompose a square into? And answering this question takes a slight realization, a small realization. But first we want to observe the ones that we already know we can, right? We have one square. That's good. A square is already a square, so we don't have to think too hard about that. And as you saw in the short, we can divide this up into any number of perfect square numbers, right? 2 by 2 is 4. We can do 4 by 4, which is 16, right? And of course, I could erase these lines and draw 3 by 3, 5 by 5, etc. So we can get any of the perfect squares. I mean, that's literally what they are, right? They're squares, so we should be able to make a square out of these numbers. That's all well and good. But what about all the other numbers? What about 2 and 3 and 4 and 5 and 6, 7, 8 and all the numbers in between, right? Can we make any of those numbers? And are there any that we cannot decompose a square into? Well, yes. There are plenty more that we can do. In fact, we can do infinitely many, and there are only finitely many squares that we cannot decompose a square into. So let's see how we can figure that out. So we know we already have all of those. Let's see, can we come up with a way of generating more squares from answers that we already have? Well, let's take a look at this. So we know that I can turn a single square into 4 squares, which means whatever my solution is that I already have, I can take a square in that solution, chop it up into 4 squares, thus I have increased the number of squares by 3. So no matter what solution I have, I can always add 3 to it. So as soon as I can prove that I have like 3 different numbers that are all, different remainders when divided by 3, the fact that I can always add 3 means I can create basically any amount that I want. So let's see, how can I create, say, look, I can just do this simple division again. And you'll notice I now have 7 squares, right? So I'm able to decompose a square into 7 squares. So I can definitely do 7. And since I can add 3 by decomposing any square into 4 squares, that means I get 10 and 13 and 16. I can always add 3. I know I've already got 16, but the point is I can do all of those. And I also have 4, right? And I started with 4 and 1, so that's sort of all of the numbers that are, one more than a multiple of 3, right? 1, 4, 7, 10, etc. I can do all the numbers that are 1 more than a multiple of 3. But what about a number like 6? How would I do 6? Well, let's observe the opposite phenomenon, right? I can take something like the solution with 9 squares, terribly drawn, I know, but I know I can do 9, right? That's what it's a perfect square after all. And I can undecompose a square, right? Here we have a grid of 4. I can simply undo that, and now look what I've got. I have a square decomposed into 1, 2, 3, 4, 5, 6 squares, which is exactly my goal. So now I've got a multiple of 3, 6, and since I can add 3 to any number, I now have every multiple of 3 after that. I have 6, 9, 12, 15, 18, 21, and so on. I know I can do any of those because I can always take any square in my solution and decompose it into 4 squares, which adds 3 to the total. So we've gotten quite a lot here, but there's still an entire class of squares that are missing. For example, we don't have the number 8, right? If I can get 8, then I'll have all the numbers that are 2 more than a multiple of 3, except for the really small examples. But let's see if we can figure 8 out. So how can we do 8? Well, again, we want to maybe analyze another example. So let's take a look at the solution with how many squares? Let's take a look at the solution with 16 squares. So that would look like this, right? Chopped up into a 4 by 4 grid. And just like I can decompose any square into 4 squares, I can also decompose any square into 9 squares, right? We've seen that it's a perfect square number of squares, so we can do that. I can also undecompose 9 squares back into 1. So I could take these 9 squares right here and undecompose it, because I know they form a perfect little square here by construction. And now you'll notice I have 1, 2, 3, 4, 5, 6, 7, 8 squares. And from here, I can chop any of these squares up into 4 squares, thus always adding 3. So I can do 8, I can do, what's that, plus 3, 11, 14, and so on. All the numbers that are 3 more than these, like so. So I have been able to show that we can do all the squares, which is of course they're perfect squares, and starting at 1, 6, and 8, which is 1 more than a multiple of 3, 0 more than a multiple of 3, and 2 more than a multiple of 3, I can add 3 to all of those as far as I want. So there's only now finitely many numbers that we haven't figured out, and that would be 2, 3, and 5, right? So those are the 3 that we haven't explored yet. Every other number is completely covered, right? 1, no 2 and 3, here's 4, no 5, here's 6, 7, 8, 9, 10, 11, 12, 13, and so on. We've hit every number. So the only ones left to consider are 2, 2, 3, and 5, okay? So let's see if maybe we can prove that we can't do that. Well, there's something we want to observe about squares, right? They have 4 corners. Every square has 4 corners. So either, what you'll notice about any of these decompositions is either the decomposition has 1 square, in which case it's the solution with 1 square, it's the trivial solution, and that 1 square covers all 4 corners of the square that we're talking about. Otherwise, we're going to need at least 4 squares in our decomposition, or else we won't be able to cover all 4 corners because, well, we need at least one thing tucked in each corner. So if we want to ask about 2 or 3 squares, that amount is simply going to be impossible, because no matter how we increase the size of these little squares to maybe fill up the whole image, there's still never going to be a square tucked up into this corner. So by that argument, 3 is not possible. No 3s. And by the exact same reasoning, 2 squares is also not possible, right? Because I only have 2 squares tucked up into 2 corners, and no matter how I increase or, shrink the size of these 2 little squares to fill in the larger square, I'm never going to be able to get anything tucked into these corners. So 2 is also not possible. So the only thing that leaves is 5. Is 5 squares possible? And we can immediately see from the drawing I made before that it isn't. Because if we had 5 squares, we already see that 4 of them will need to each take 1 corner. But now I think it's probably clear to see that no matter how I enlarge or shrink these 4 squares to sort of fill in the larger square, the remaining space that we have is always going to be this funny cross shape in the middle, almost like a flag. And that funny cross shape is, well, clearly not a quadrilateral, so it's definitely not a square, right? There's no way to move, shift and squish and stretch and change the size of these 4 squares to make a square shape that's left over. So I will never be able to use a 5th square to fill in the rest of the space, and so 5 is in fact not possible. You can deconstruct a square into as many squares as you like, as long as that number is not 2, 3, or 5. Thank you very much.